Alright, this is 3.4 notes, measures of relative standing and box plots. So, big key concept here is this idea of relative standing, which basically is saying how things relate to the mean or how they relate to one another. And one of the most important topics we talk about all semester is the z-score. Now we will introduce it this time, and then it's going to seem like we forget about it completely, but trust me, we definitely come back to the z-score at the end of the semester. And then the box plot is the other big thing that we talk about in this section. Alright, the basics: z-scores, percentiles, quartiles, and box plots. Percentiles and quartiles are kind of one and the same, and then box plots are like a visual of this idea called a 5-number summary. So the z-score. The z-score, sometimes called the standardized value or the standard value, this gives us a measure relative to the mean. Alright, its value x, which is kind of misleading, we use z a lot of times to represent it as well, but it's a value a plus or minus. It's basically like if we make the mean 0, a positive z-score means you're above the mean, a negative z-score means you're below the mean. So the z-score is just a relative position to the mean. Alright, and the formula for the z-score is as follows. We got the measurement minus the mean divided by the standard deviation. In both cases, it's just, this is the mean for a sample, this is the standard deviation of a sample. This is the mean for a population, this is the standard deviation for a population. Okay, but they're the same notation. Alright, and it tells us to round z-score to 2 decimal places. Alright, so z-scores, again, all they are just measures how far something is from the mean. Okay, their units are, they're unitless, but they are really measured in standard deviations. If you get a z-score of 2, that means that measure is 2 standard deviations above the mean. If you get a z-score of, if you did this formula and you got a z-score of negative 2.5, that means you're 2.5 standard deviations below the mean. Okay, so they're a measure of how many standard deviations something is above or below the mean. Alright, and then interpreting z-scores, we kind of hinted this last section, but remember, if a z-score tells you how many standard deviations something is away from the mean, then 2 standard deviations or more above or 2 standard deviations or more below the mean is considered unusual, and then anything not in that range is considered ordinary or not unusual. Okay, so that's just summarizing what we said in the last section of notes, except we didn't call it z-score, we said however many standard deviations something is above or below the mean. Alright, so here for an example, test scores on a certain test had a mean of 78, a standard deviation of 11. So would a test score of 93 be considered unusual? What about 45? So basically what this is asking me to do is find the z-scores here. So if I take the z-score for the first one, 93, that's x minus the mean of 78, and I divide by the standard deviation of 11. Right, 93 minus 78 is 15, and then 15 divided by 11 is 1.36. Alright, remember we round these to 2 decimal places, so 1.36. Okay, now what about 40? Oh, so is that considered unusual? No. So this would not be unusual. Remember, it's unusual if it's greater than 2. Alright, not unusual, or I guess we could say it's usual. Alright, and then the other one, the second z-score, now 45 is our measurement, so we subtract the mean from 45, and then we divide by 11. So 45 minus 78 is 31, negative 31, divided by 11. And then negative 31 divided by 11 is, negative 31 divided by 11 is negative 2.881, and so this is less than -2, so that would fall right around in there. So this would be considered unusual. Okay, so that's what we mean by the z-score. It's a measure of how it compares to the mean, and because we're dividing by the standard deviation, it tells us exactly how many standard deviations this is above, positive, or below negative the mean. Alright, then percentiles. Percentiles tell us the percent of data that are below a value. Okay, the second percentile means there's only 2% below that number. The 99th percentile means 99% of the data values are below that number. Alright, this is the way that we compute it. We take the number of values less than that value, divide by the total number of values, and we get 100. Okay. Alright, so for example, if we wanted to find out what percentile this number was, 31, we count up how many values that are less than that. There's 1, 2, 3, 4, 5, 6 values less than this number. Alright, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total. And we multiply that by 100. Alright, and that equals the 60th percentile. Okay, so 31 is the 60th percentile, or with the notation P60, the 60th percentile is equal to 31 in this case. Okay. Alright, so quartiles are specific percentiles. Q1, the first quartile, is the 25th percentile. Alright, the second quartile is the same as the median because it's the 50th percentile. 50% smaller, 50% larger. And then the third quartile is the 75th percentile. Alright, 75% smaller, 25% larger when you're talking about the quartiles. So they are specific percentiles. Alright, then this is the notation we use again. Q1, really Q2, we just call that the median. Alright, so I just use MED for Q2. And then Q3. And if you look at it, it's kind of like the minimum value in a data set is like Q0. Alright, and then the 1, the 2, the 3, and then the maximum would be Q4. And the 1, 2, 3, 4 are how many quarters or 25% chunks that you've accounted for. So no 25% chunks, 1, the 25% below it, 2, the 50% below it, 3, 75% below it, and then Q4, everything's below it. Alright, so that's kind of the way that the little subscripts break down and what they're used for. Alright, and then another important statistic is the interquartile range, Q3 minus Q1. Alright, I'll show you some examples for that in another video. Alright, the 5-number summary. It's really important for box plots. That's basically a box plot is a visual of this. But when you have the 5-number summary, the 5 numbers are the minimum value, the first quartile, the median, the third quartile, and then the maximum value. Those are your 5 numbers in the 5-number summary. Alright, and then if you make a box plot, you're making a visual of that 5-number summary, okay? Because you're making a box that goes from the first quartile to the third quartile with the median in the middle, and then you have a line extending out to the minimum value and the maximum value. So basically they look like these rectangles. Your whiskers is what we call them sometimes, go up to the maximum and minimum values, and then somewhere in the middle of the box you have the median. So a box plot has those 1, 2, 3, 4, 5 numbers from the 5-number summary as their major points on the box plot. Alright, and so just so you'll see, this is a better visual, kind of blown up. There's the minimum value, Q1, Q2, or the median, Q3, and the maximum value. Now a box plot, if it's nice and symmetric, if you have a bell-shaped curve, your box plot will look symmetric, meaning that the left whisker will end, it'll be the same roughly length as the right whisker, and your box will be kind of right in the middle of those two whiskers, and then the median, the line that represents the median, will be right in the middle of the box. So if you have bell-shaped data, then your box plot should be roughly symmetric, just like the bell curve would be. But if you have skewed data, all right, this is data that would be skewed right. You would have a longer whisker to the right, and not only that, your median would be over to the left side of the box, meaning that there's a bigger space on the right side of the box than there is the left. So this is right skewed, all right, or positively skewed distribution. And it's definitely not symmetric when we see this extremely long whisker, and not only that, but the median pushed to the left or the right in the interquartile range box. That lets you know that you have skewed data. Now if we have outliers in a data set, we can modify our box plots to show those outliers. Okay, an outlier is a value that's extremely large compared to the rest of the data, or small. It could be much smaller than the data. Outliers really affect the mean, the standard deviation, and that's because both of these formula use all the values in the data, so they're going to use that outlier when they are computed. So an outlier will also really skew the effects of a histogram and a box plot. So what we do a lot of times is we modify it, and we define an outlier by that interquartile range. There's the IQR for interquartile range. And we take any value, we take Q3 and we add to Q3 1.5 of these interquartile ranges. And if you do that, 1.5 times IQR, we call this the upper fence. And anything beyond that is considered an outlier. And then we do the same thing for the lower fence. We take Q1 and we subtract 1.5 of the IQR. And that'll be our lower number. Anything below this is considered an outlier. Alright, so we can have outliers above if it's above this number. You can have outliers below if it's below this number. And again, I'll show you some videos, examples in the next set. Alright, and then if we modify our box plot, we use dots to represent the outliers. So we don't make the whiskers go to the largest and smallest values necessarily. We make them go to the largest and smallest values that are less than these two values. And then we use dots for anything that are beyond these two values. Alright, so here's an example. Here's a modified box plot. So this has the pulse rates. So this has you know, a Q1 looks like around, let's say 68. It has a median, let's say, of 73. It has a Q3 of 80. It has a minimum pulse rate of around 59, we'll say. And then it has, instead of this going all the way to the maximum pulse rate of around 124, or this one here about 104, and then this one here, let's say that's 97. Okay, so what we're saying is this 104 and this 124 are outliers. This is a better predictor of where pulse rates will fall, and these are our outliers that are falling well above where the rest of the data is falling. Alright, so if we have outliers in a data set, we don't want to just throw them away because they're skewing our data. We want to show them, but if everything else is falling in a tighter window, then sometimes we'll modify our box plots to show that everything's kind of falling here, rather than to have this really long whisker that suggests, you know, maybe that the data is very skewed, when maybe it's not all that skewed other than these couple of outliers, because this median is, you know, almost perfectly centered in this box here. Alright, so that's a modified box plot. Again, I'll show you some examples later how to make these by hand or on your calculator.